Today, scientific notation, which is actually pretty easy. What makes it difficult, though, is that it's a new concept for some people, or a concept they haven't been around a lot. So it's not so much the actual writing of it or the converting of regular numbers into scientific notation, or vice versa, that is a problem. The issue that people have typically is just the strangeness of it because it seems kind of new. So the concept is pretty easy, but it's just getting your mind around thinking of numbers in this way. So don't worry too much about it. It's pretty simple, and we're going to take off. No problem. On the board here, you see I have different numbers. Here I have whole numbers that are not complicated, even though that one looks kind of complicated. Then over here we have them in the scientific notation formula already. The scientific notation is already there, and we're going to transfer those into normal numbers as we go. And then there's some stuff in the middle we're going to do here. But scientific notation, the point of it is to put really huge numbers, numbers that are really long with a lot of digits, into something that's more usable in mathematics or chemistry or physics or whatever we're doing. Whether it's a real huge number, 93 million, or it's a real tiny, tiny, tiny number. That's a decimal there, so this is a very tiny, tiny number. But they take up a lot of digits, so as to simplify it. The formula overall is number dot number times 10 to the blah. Number dot number times 10 to the blah. And that's the way it always is. The number here always has to be between 1 and 10. It's always going to be between 1 and 10. This here. It's never going to be 12 times 10 to the something. We can make it smaller, like 1.2 times 10 instead of the 12. It's never going to be less than 1, so it's never going to be like a decimal like 0.5 times 10. It's always going to be bigger than 1, so we would have just the whole number 5 times 10 to the blah, blah. But we'll get to that here in a second. So number dot number times 10 to the blah. Number dot number times 10 to the blah. So let's look at how to convert these. 740, not a real big number, but I'm just using something that we're kind of more familiar with. We wouldn't be familiar with using these all the time, but 740 is not too bad. So I'm going to use that to illustrate how we go about this translating between standard notation, whole numbers and such, and scientific notation. So what we do is notice there's a red decimal here. Hopefully it shows up on the film. That's where the decimal would be, even though we don't write it at the end of whole numbers. But where do we want the decimal to be? Where we want the decimal to be is right between the first two numbers, if there are two numbers. If there's more than two numbers, we just put the decimal after the first number, and then whatever numbers until the zeros start. But in this case, we just want it to be here. That's where we want the decimal. That's where it was. So from there, we zoop our way back to where it was. So we start here, zoop, zoop. So that was 2. So no problem, we just have 2 zoops. So the number dot number is the 7.4 number dot number, and it's always times 10. Times 10 to the something, times 10 to the blah. So number dot number times 10 to the blah. So what of the blah here? Well, here we moved 2 to the right. So it would be 2. No problem. The way we know it's positive is because there's actually 2 ways. There's more than 2 ways, but 2 easy ways. One, if the number is big, if it's bigger than 0, then no problem, it's positive, because it's a bigger number. If it's less than 0, like this thing, if it's less than 0, then that's negative. That's one way. If it's big, it's positive. If it's small, it's negative. On the other hand, if you think of a number line, then you go 1, 2, 3, 4, 5 out this way. These are the positive numbers as you go this direction. 1, 2, 3, 4, negative 5. As you go this way on the number line, that's negative. It's the same here when you do it this way. When you go from what it needs to be to what it used to be, we're going to the right. So we're going to the right, it's positive. So that might be a couple ways for you to kind of think of it. So that's this one. Let's try this one. Again, where's the decimal? It's here at the back. But where do we want it? We want it, that's where it is now, we want it to be between the first 2 numbers. Now again, if it was just 10,000 with a 0, you just put the decimal there still, but when you would write it, you just leave off that decimal, so it'd be 1 times 10 to the blah. So we go here, we go where it is and where it was, and we zoop. 1, 2, 3, 4. And do the zoop. It'll slow you down so your eyes don't play trick on you. Imagine if you had to count all those. It'd be really easy to mess up, but if you're zooping it, it slows you down just enough so your eyes can't play tricks on you as easily. So we have 1 1.8, number times 10 to the blah, times 10 to the 1, 2, 3, 4. 4, is it positive or negative? Well, it's a big number, so it's positive. Or you can think, well, we're going to the right, and that's positive. So it's 1.8 times 10 to the 4th. Well, what if there's this ugliness? By the way, this is how much an electron weighs. So if you ever need to get rid of your electrons, take them to the dump, you need to calculate how much it's going to cost, you know, I'm just kidding. So we're going down here, we do the same thing. We do, where is the decimal now? It's here. But where do we want it to be? We want it to be there. So it's 9.1, and we know it's times 10 to the blah. Oh, no, zoop a long ways. So this is where it is, that's where it was. Start where it is and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. To the 31st. Was it positive or negative? Well, it's a very teeny, tiny number, so it would be negative. And we're going from here to there to the left, so again, that would be negative 2. So the weight of an electron in kilograms is 9.1 times 10 to the negative 31st. And yes, there really are applications and really are times that people need this. I used to need this in what I used to do in the Navy. We would need to know those kinds of things. So going back over here, let's go the other way now. So we have 2.74 times 10 to the 5th. Again, it's already written in scientific notation. Number times 10 to the blah. We already have that. But we need to get to, well, what's the number going to be, really? Well, we start here, 2.74. And that's where it is, but where we need it is 5. It's positive. So it's positive, we're going to make the number bigger, or we're going to move to the right, because that's where the positive is. Same thing here. So we're going to go 5 and do the zoops again, and you'll see why here in a second. 1, 2, 3, 4, 5. That's where it is. That's where it was. So when you go back here, well, what do we do with all that space? Well, sure enough, it looks like it's just asking for a little 0. And sure enough, it is. We just put them in there. So we go in there and we add the zeros. 1, 2, 3. And then we can do our commas. So 274,000 is that number that would be there. Easy. Then, of course, you'd rewrite it without all your zooping ugliness all over it. So we go to the next one. 8.1 times 10 to the 4th. Let's try that again. So we have 8.1 times 10 to the 4th. And it's a positive, so again, we go to the right. Or we know it's going to be a bigger number, and going this way would make it bigger, going this way makes it smaller. So we go 1, 2, 3, 4. Put the decimal there. Then we fill in the zeros. 81,000. And then here we have a negative 1. So we start there with the negative. It's just a 3. Oh no, there's no decimal. What do we do? Well, earlier I was talking about if there's a whole number, that's fine. It's between 1 and 10. There's just nothing there. So you just put 3, and the decimal is there, even though we don't write out a whole number. But times 10 to the negative 6. Oh, negative 6. Negative. So we need to make it smaller going this way. Or to the left is negative. So we go 1, 2, 3, 4, 5, 6. That's where the new place of the decimal is. That's where it was. So then we go back in there and we go 1, 2, 3, 4, 5. So the new number would have 1, 2, 3, 4, 5 zeros. And your 3. And that would be your answer in standard notation. Now why did I write this? That's a familiar number to some people. That is the approximate distance from the Earth to the Sun, 93 million miles. But if we were wanting to write that and actually calculate some things, like, well, if we were flying in a rocket at the speed of light, how long would it take to get there? Or if we wanted to say, well, how long does the light or the heat from the sun, the light, take to get to the Earth from the sun? It's like, well, we wouldn't use this number. That could get real ugly. So we do our scientific notation thing, 9.3. There you go. This is where we want it. And we go all the way to the end. The decimal was here. 1, 2, 3, 4, 6, 7. To get there, times 10 to the, this is where it is, that's where it was, we're going to the right to get there, and we went 7. So 9.3 times 10 to the 7th would be the approximate length of the distance between the Earth and the Sun in miles. And that's it, scientific notation. Number dot number times 10 to the blob. See you next time.